ए अंदाजा फिर मैं सुनो सेंड मी लॉगिन कर दिया हूँ IEEE से, मुझे हटाना पड़ेगा, इसको क्लोज करना पड़ेगा।
टाइम था तुम कर लो, 6 बजे तुम्हारे पास है 5 मिनट का बड़ा स्विच ऑन करो वहाँ पे,
कैसे?
वहाँ पे स्विच करो, दूसरा पेज से।
नाइस, थैंक यू। मुझे कोई अलाउ करो। हाँ दे दो दो। अरे
जो मेल है ना उसी कॉपी पेस्ट कर दो।
I think we will start. Professor, can we start?
Yes.
Sir. Okay. Good evening, everyone. Today, Dr. Krishna Fajar with us for the invited talk. Thank you, Professor, for accepting our invitation for giving the lecture. Invited talk with our IEEE AP-MTTS student branch chapter, IIT-KGP. So, Christian Fajar received his PhD degree from Chalmers University of Technology, Sweden in 2003. He is a full professor at the same university and from 2020, the head of the microwave electronics laboratory. His research focuses on transmitter for future wireless systems. Dr. Fajar has authored and co-authored more than 200 papers in international journals and conferences. Dr. Fajar currently serves as an associate editor of IEEE Microwave Magazine, IEEE Microwave and Wireless Component Letters. Thank you, Professor, for accepting our invitation. Now you can proceed.
Thank you very much. It is my great pleasure to have this opportunity to speak to you, give a presentation to you about what we're the kind of research that we do at Chalmers. And our research is, in my case, oriented around transmitter design challenges in emerging wireless communication systems. So I want to start by giving a short overview of where I come from. So just for your information, here is we're located in Sweden and particularly on the west coast. So Sweden and particularly Gothenburg, where Chalmers University is located, has a long history in microwaves. It was founded in 1829, but the history in microwaves is very strongly connected to radio astronomy, actually. So we started in the 50s to build big telescopes for radio astronomy, and from that, microwaves was established as a key research direction at our university. For the moment, we're organized in a way that I'm head of the microwave electronics laboratory. So I want to give an overview a little bit of, on a high level, the research activities that we do at Chalmers in this field. So actually, in our laboratory, we span all the way from semiconductor materials. We have people doing research on gallium nitride material research, to device design. We have a clean room in our building where research on transistors for RF, millimeter wave, and DC applications is being carried out. We work and have a very long tradition in modeling gallium nitride transistors, and actually all kinds of transistors as a way to link the device design to the circuit behavior. Reliability is another important research area, thermal effects, and all of those is of course used when we build the circuits. So a big activity and the focus very much of my talk today will be about circuits. So we do research on circuits both at low frequency, but all the way up to terahertz frequency range in different type of semiconductor technologies, and I will come back to that later. But the circuits need to be often put in modules and packaging, so this is another important research area for us. And we need to look at the signals that are fed to the circuits that we want to characterize. Of course, we rely a lot on measurements, all kinds of measurements from component to circuit to system level. And in some cases, we also carry out demonstrations of subset or RF systems, subsets of RF systems. So that's the microelectronics laboratory in a nutshell, from materials to components and systems. And we are very well equipped in terms of lab facilities. We have very capable microwave and terahertz labs, one of the best equipped labs in Europe, I would say, for being in a university. But we also have a nanofabrication laboratory where we do the clean room processing. All in all, in our lab, we are around 35 people, 4 professors, researchers, PhD students, and adjunct and affiliated professors. So this is the microwave electronics laboratory at Chalmers. And I'm here the head of this laboratory, and I'll give you a snapshot a little bit
नहीं देते हैं
of what we do.
जो लोग हम लोग सब्सक्राइब किया ना यूट्यूब में
And in my
YouTube channel में
specific
उसको
case, I have been
दिख जाता है,
focusing
like
on
कि
transmitters for a long time. And
YouTube?
transmitters, I say that because it's not only about power amplifiers, it's all the way from antennas, signals, and circuits. Because nowadays the trend is towards, as you know, active antenna architectures, because they play a fundamental role in modern communication and sensor systems. In millimeter wave frequency, which is a hot topic today, and in sub-terahertz, also by the way, most often this translates into phased arrays, or in some cases hybrid beamforming implementations. But we are also interested in lower frequencies, sub-6 for example, sub-6 gigahertz, where we really can talk about digital beamforming and massive MIMO systems. Of course, all those systems promise a major increase in capacity, but also an increase in energy efficiency, because we can direct the energy to the directions where the users are located. Of course, in order to realize such energy efficient systems, we need to integrate much more than before we need to co-design, I should say, between circuits, antennas, and signal processing. This happens at millimeter wave, but of course also to a very large extent at RF frequencies. So we're going into a direction where circuit people need to understand antennas, antenna people need to understand circuits, and signal processing people need to take the hardware effects of circuits and antennas into consideration. So there are many good opportunities now for collaboration across domains that were previously separated. But it also raises new challenges in the design. And I will go here into some of the challenges in transmitters particularly. So one of the main challenges when we integrate circuits, antennas, and so forth is the power dissipation. The power dissipation is something that has to be handled. So we need to have the most important way for doing it is to look at efficient power amplifiers. So previously, power amplifier efficiency was driven by the need to reduce energy cost. But I would say that today, the driving force to get high energy efficiency in amplifiers is to reduce heat dissipation. If we cannot get cool or low heat dissipation in the power amplifiers, we cannot integrate the active antenna systems that we would like to build. We also need to understand how various hardware impairments affect the performance. We need to understand how circuits, antennas, and signal processing, how they have to be jointly designed to get the desired signal into the air. That brings the need for new modeling techniques, but also multi-physics modeling, where, for example, the heat dissipation has to be considered. Linearization is our means to correct for some of the impairments that we see. So linearization can happen both by analog implementations, so analog linearization, or digitally, both for single antenna systems and in MIMO cases. And finally, I want to say some words about something about beyond 5G or 6G communication. There is a trend from antenna arrays into distributed antenna systems, and I want to say some words about the work that we do in that area. So I will, by the way, I will go through this presentation and I hope to finish roughly in 45 minutes. So if you have any questions, we can probably take them best at the end. All right, so talking about power dissipation. Here we have the topics of efficient power amplifiers and thermal coupling. In our university, or in our group, we have spent a lot of time to investigate new innovative power amplifier architectures. And as you know, or as you may know, the main objective of power amplifier design is not to get high efficiency at peak power. Here is the plot of efficiency versus output power. Getting high efficiency at peak power is important, but it is even more important to get high efficiency at low power, because the probability of the signals that we want to transmit look like this. Almost none of the time is spent at highest power. Most of the time is spent at the lower power. So efficiency in this regime is what matters. So we look for architectures that have this kind of characteristic. So, and that means that we have to, of course, in different applications, look in different architectures. Looking at high efficiency, obviously, we are looking at innovative circuit architectures. This has to be operated sometimes over multiple bands or large concurrent bands. We need to look at highly integrated power amplifier solutions, and we need to look at high frequency operation. So all these different directions result in different trade-offs, and new innovative architectures will be needed. So I will give now some examples of recent research that we have been doing in these different directions. So here is one example, and made by previous PhD students here. This is about Doherty power amplifier design. Doherty power amplifiers are, as many of you know, a very well-established architecture for achieving the characteristic that I showed before. What we have done here is to develop a technique to synthesize the combiner. This is, as you can see, an integrated circuit at 28 gigahertz. And how to design the combiner between the main and auxiliary branches in a Doherty amplifier is the key to get high performance. We developed a theory to synthesize this network analytically instead of more empirical approaches that were done before. So by doing it analytically, we can reduce the losses and get higher efficiency than in other implementations. So here's an example where you can see efficiency is in the order of 30%, even at 6 dB back off. And this is quite old result, and we have seen much better results more recently using this technique. So, and here you can see an implementation. This happens to be in silicon germanium at 28 gigahertz, but the same technique presented in these papers. This paper is applicable to all frequencies, independently of, and all technologies, independent of the application. We have recently extended this work from 2 branch to a 3 branch, or 3-stage Doherty. You can see that the 2-stage Doherty is normally having 2 peaks. If we can extend it to 3 stages, we can get an increased efficiency over a larger output power range. And again, we developed a theory to analytically synthesize this combiner network. So from the load pool data of the transistors, we can put it into equations and arrive at the network acting as a combiner. So this network was analytically calculated, and we can connect the 3 transistors here, here and there into this network and achieve this performance. We really can see distinctly the 3 efficiency peaks corresponding to here. Another interesting architecture that we have been studying recently is to use a circulator as a combiner. As you can see here, the idea is to have 2 amplifiers again, but as a combiner we now use a circulator. The circulator is of course a very unusual combiner component, but it is interesting to see that actually it can also act to realize a highly efficient power amplifier design. So the advantage of the circulator is that it is relatively wideband and has relatively low loss. The drawback is that it is difficult to integrate. But even from the prototype we have achieved with off-the-shelf components, you can see here that we maintain a very high efficiency, close to 50%, over a very wide frequency range. So this is still ongoing research, and we have more results soon to come. Another important aspect when it comes to power amplifiers is to investigate how it can be integrated or co-designed with the antenna. Traditionally, we have the situation to the left where a power amplifier, in this case Doherty amplifier, is designed separately. So we have a main and auxiliary amplifier, we have a circuit combiner, we have a 50 ohm interface, and then we have an antenna. This is the traditional way to build a system. However, it turns out that actually the antenna, or rather the antenna element, can serve two purposes. If you design the antenna element in a clever way, it can actually act simultaneously as a combiner and as a radiator. So we have the situation to the left, to the right, where we, by choosing the feed point in a good way, can actually make it work as a joint efficient transmitter. Of course, this is very compact and will have very high efficiency. So we made demonstrations at 2 and 3.5 gigahertz. These are prototypes, I should say. This was the initial prototype, and this was the more improved variant, where you have the combining functionality on the patch, but also filtering functionality in the same block. And the challenge here is also sometimes how you do the measurements, because there is no point to connect a measurement equipment, so we need to make the measurements in an anechoic chamber or in a reverberation chamber. So that's what we did. We put the device and the test in a chamber, and we compared the results from simulations and from an anechoic chamber and reverberation chamber. And as you can see, there is relatively good agreement between the three different ways of predicting. So, and as you can see, we also get a very high efficiency, close to 60% over a large output power dynamic range. So that's a very interesting direction, I should say. What I can also say is that to take this one step further, we have here looked at the analog domain, where we combine the analog components, circuits, with the radiator. In the next step, we need to look at the left side, how do we generate the signals into this? So we have an interest in, and in particular this is important when we talk about efficiency. We can maximize the efficiency of the analog components and the antenna, but at the end we also need to take the energy consumption of the digital components into consideration. So we have actually also research going on highly integrated digital transmitters. So that's what I'll show next. Because here we can see how we have integrated digital and RF, or I should say millimeter wave functionalities, on the same chip in CMOS. So what you see on this chip is actually a IQ modulator power amplifier. So it's an IQ modulator co-designed with the power amplifier and D to A converters. So it's actually, it contains two D to A converters, you can see here, mixing with an RF signal to generate an IQ modulated millimeter wave modulated signal. So it's a rather complex digital or mixed signal circuit comprising an LO input and this analog or joint analog digital circuit, and actually an on-chip memory. And this memory is very essential because the memory here contains the waveform that we want to transmit. So rather than relying on external instruments to generate the communication signals, we here have made our own, you can say, measurement instrument on the chip. Because at these very high bit rates, we talk about 11 gigasample per second, it is very challenging to feed digital signals onto the chip. So by placing the memory and the DACs on the chip, we can investigate the energy efficiency and linearity in a much better way. So what you can see here is a demonstration of the performance, for example, demonstrating 8.5 gigabit per second at 6.4% EVM in a 64 QAM transmission. And here you can see the wideband operation covering a few gigahertz of bandwidth and a very good ACLR performance. And this is in itself an enabler for high density and energy efficient millimeter wave active antennas in the future. Right? So having this as a background, I want to take the next step, because okay, we can have building blocks for the amplifiers and so forth, but at the end what we want to build is an active antenna. So we need to understand how to, in order to design good circuits, we need to understand how the circuits behave when they are connected to an antenna. And that's the next area of my presentation here. Because if we look at how systems are built, they are typically built assuming a 50 ohm interface between the different components. If we have 50 ohm, it is very straightforward to cascade components and realize complex systems. For example, power amplifiers, filters, antennas, if they're all 50 ohm, we can very easily connect them together, and if they don't 50 ohm, we can put isolators in between and so forth. We can also easily measure and generate signals using 50 ohm standardized equipment. The challenge now is that as we move towards more highly integrated transmitters, we are facing a situation where we no longer can guarantee a 50 ohm interface. Our circuits, which often are chips, if we talk about high frequency, they can be embedded in complex electrical environments. We can no longer guarantee that they see a good 50 ohm, and there is no way for us to put an isolator or something like that in between. So essentially, we need to live with a non-50 ohm environment to the circuits. Since we have to live with it, we also need to understand what implications this has on the antenna array. In consequence, we need to look for models, system models, where, for example, power amplifier circuit models are having not only one input signal, as usual, but they may also be exposed to input signals at the output, reflections from the antenna, for example. So A1 and A2 become inputs, and we should predict B2. And so normally A2 is neglected because we have a matched system, but if it is not, we have to take it into consideration. So we proposed some 10 years ago a model for this, which is essentially an extension of the what is called X parameters by Keysight, but with memory and more suitable for system level simulations. So here you can see development. You don't need to look into it in detail, but you can recognize that the model essentially contains S21, S22, and something called T22, which is needed in large signal operation. So essentially nonlinear S parameters and this T22, which is also part of the X parameters to make it consistent. So with those type of models, we can put them together with an antenna array to form a simulation framework for active antennas. The signals feeding the power amplifiers are given by, in a MIMO case, it's a precoder. If it's a phased array, it's simply phase shifted input signals of the same. On the other side, we can predict from the antenna modeling the radiated signals, and thereby establish the relationships from the input to the user signals at the remote location. So if I take as an example a phased array, here you have an example where the input is now phase shifts of the same signal, where the phase shift is controlled by the steering directions theta and phi. So the input signal is A1 with those phase shifts, and this is the model S21, S22, and T22. And the antenna S parameters, they establish the relationship between the waves going in and out to the antenna. This is a linear, antenna is a linear part. If you solve this equation, or if you set it up, you see that you will have the regular 50 ohm nonlinear distortion, but you also have a second part, which is due to the antenna coupling and mismatch effects. And I will come back to that antenna coupling and mismatch effects later on. But essentially, if you solve this, you can predict B2, and B2 is then the excitation of the antenna, and the antenna, as we know, is a linear device, so we can apply superposition. So from the superposition of the embedded element patterns, EI, we can get and predict the modulation of the signal in any direction in the air. And obviously, ideally, this signal here should be the same as we put in here. So here is an example of how this is used. We have made a model of the type I showed you before for a gallium nitride power amplifier. We have an antenna array that we obtained from Ericsson. It's a 64 element array, and we can now predict the EVM, that is the distortion in the far field, as a function of scanning. And this is the result. So here you can see scanning in azimuth and elevation, and the color here denotes the distortion. Blue is low distortion, red is high. And why does it not stay constant? Well, if you look at it, or actually we can make use of the architecture that we proposed. Here is the possibility. If we take the ratio between the B2 and A2 waves, we can get the impedance. So the reflection coefficient or the impedance seen by the PA into the antenna looks as follows as we scan. So certainly the impedance is really, because of the mutual coupling, dependent on the scanning. And as you can see, a central element faces a certain degree of influence, an edge element something else, and any element actually will have a different load variation. So that load variation is in turn affecting the behavior of the power amplifier. So if you look at it in a specific steer direction, and I can choose to take the direction where the distortion is low, we can now study the resulting 64 branches in this array and the AM for each of them. And you can see ideally this should be flat, but some cases here you see it is expanding and some is compressing. And I should say this expansion and compression is from a linearized case. So some antennas are actually overcompensated for some branches. Some branches are undercompensated. But in average, from the 64 branches, we have an overall relatively constant gain profile. So the distortion is actually averaged in the array in that direction. To the right, you see which antennas are expanding and which antennas are compressing. But you can see that in overall, it's close to zero. If we then steer in another slightly different direction, the situation is completely different, and all amplifiers are actually expanding. All of them are expanding, and therefore obviously in the air there will be an expansion as well. So this is just an illustration of what happens in active antenna systems as a function of scanning. And the result is that linearity needs to be will be direction dependent. We have carried out some experiments, and this is now for a very small scale array using beamforming chip to predict the far field and the distortion in over-the-air measurements. You can see the antenna array and you can see the receiver a bit away. And we can predict the received power and AM/AM compression, for example. And you can see that it's relatively good agreement between the different cases, just validating the simulation. This is still something that we have many things going on with, but I wanted to show you the framework, which is very generic and can be used for all kinds of applications. And in fact, our next step is to extend this framework to also extend heating, to include heating. If you remember from before, we predicted B2 as a function of A1 and A2, but in fact B2 is also a function of temperature. So temperature is affecting the gain. On the other hand, the power dissipation is also a function of input power, and the power dissipation is resulting in heat. So if we have a model describing how heat or how temperature depends on the dissipated power, we can close the loop and make this simulation also take temperature variations into consideration. So here we need to look into thermal modeling, and these are models that we make using, for example, multiphysics tools like COMSOL or IcePack, ANSYS IcePack. We need to look into circuit modeling, both AM/AM type of models, gain models, but also power dissipation models. And we need to look into antenna models, both in terms of S parameters and in terms of radiated fields. So when all of these are combined, we can make many interesting investigations. For example, looking at transients of temperature when we switch on the antenna array. And this happens, for example, if you switch from transmit to receive. We can look and see how is beamforming affected by neutral coupling or by heat. And we can study how the far field dynamics, the dynamics of the distortion as a function of self-heating. And of course, reliability in terms of mechanical, thermomechanical stress. All of these are effects that can be covered by the proposed simulation environment. Okay, so now I will move to the third part of my presentation, because now we have seen that there is a problem. There may be problems of linearity caused by the power amplifiers themselves, but there can also be new problems appearing when we put the antenna, we put the circuits into an antenna array. So if we can investigate ways of improving that linearity on the circuit or signal by using circuits or signal processing techniques, that is of course very valuable. So I will here go through analog techniques, DPD linearization on a single branch, and multiple input, multiple output linearization techniques dedicated for antenna arrays. Okay, just for everyone to set the scene. Predistortion, if you have not heard about it, predistortion linearization is a technique where we apply some kind of signal processing technique, or it could be analog or digital, to compensate the behavior of a power amplifier beforehand. So as an example, if the power amplifier is compressing, we apply an expanding function before it. And if you combine this expanding and compressing function, the total result from input to output is linear. So in spectrum domain, the desired signal has a finite spectrum. We pre-distort. So pre-distort, that is, we apply a distorted signal to the input such that the output is linear or has the desired shape. Alright, so if we start, this functionality can be done in analog domain, for example using RF analog linearization. In that case, we apply some circuit before the power amplifier. It has the advantage that it's very easy, it can be part of the PA design, but it's usually frequency tuned. One example where this was used is how we explored CMOS for this purpose. And in fact, one of the main sources of nonlinearity in power amplifiers is the nonlinearity induced by the CGS nonlinearity. So as you can see to the left, here is CGS in a CMOS transistor. And if you apply a signal to this nonlinearity will cause AM/PM distortion, which is very problematic. On the other hand, it turns out that the PMOS transistors have the opposite characteristic than the NMOS. So PMOS has the reverse of the NMOS, and traditionally we have thought that PMOS is a very slow transistor, but actually it is not. Nowadays PMOS transistors are very fast and can have the same, almost the same FT and Fmax as the NMOS transistors in modern technologies. So we can use combinations of NMOS and PMOS to achieve linearization. And that was done here. You can see this is 22 nanometer FDSY. In two cases we had an NMOS and NMOS PMOS. The characteristics in terms of gain and efficiency are the same, but you can see how the AM/PM actually is significantly improved by this architecture. Another approach would be to do the linearization in baseband. If we have cases where there is upconversion, we could do pre-distortion at the baseband components. That would have the advantage that we could reconfigure this baseband pre-distortion independent of the RF frequency and reuse it for different amplifier designs. So we designed an by CMOS baseband and analog pre-distorter function, so which is then controlled by different parameters. And in this case we demonstrated this chip, connected it by connecting it to an E-band transmitter. E-band is around 80 gigahertz, and we can then see how we can manage to get higher efficiency and better linearity by doing this design. Okay, but of course there are many different other techniques. If we go to the digital domain, we could also do a lot of interesting research. And the digital pre-distortion is when we do the same thing, but we apply the linearization on the design of the signals. So there are many different algorithms that could be used to linearize power amplifiers, but all comes down to having the best compromise, because you can make an infinitely complex algorithm which has very good performance, but it has an enormous complexity. Take a Volterra series as an example. Volterra series has very high complexity and high accuracy, but it is not useful in reality because it's too complex. So we proposed to compare different models in terms of their complexity, numerical complexity in flops, floating operating points, floating point operations, so flops. So then we can compare how the linearity performance in terms of ACPR compares for different models. So here we have, for example, the GMP, which is known to be very good, memory polynomial, and other kind of functions. So you can see that there are some of the ones that we propose, for example, the BUFs, has very good performance in terms of complexity, ACPR performance. We can also look at multi-band linearization, and all in all, we have to do this development using experiments. So here I would like to advertise a test infrastructure that we have at Chalmers. If you or any of you or your students want to perform linearization experiments, the best is if you have a lab, but if you don't have a lab, don't despair, because we have a lab that you can access for free. If you go to dpdcompetition.com, and RF Web Lab, you can actually download MATLAB files or MATLAB access functions to send data to our equipment. So our equipment allows you to send the modulated signals in and get back the modulated signals after passing through a real power amplifier. So this is very useful in research and in education. And since our start of this equipment, which was done 2013, I think, or 14, more than 1 million measurements have been carried out. And you can see on this map that it is used by a lot of people all around the world. And every day it is used almost full time. But it's an extremely nice tool, so I recommend you to play with it if you have time. Of course, we have done a research on many more different advanced architectures, but I don't think I have time to go through all of them. Just have a look yourself. I just want to wrap up here on this part by saying that if we have looked at linearization at single branch, this is what I showed you before, we also need to have techniques to linearize a multi-antenna architecture. Because if you only linearize one branch at a time, you cannot compensate for the antenna crosstalk that I showed you before. On the other hand, you cannot also linearize every branch, taking all the other branches into consideration. As you can understand, if you have 100 of branches, you will have 100 of inputs to this DPD. And that's not going to work very well. So we proposed a more scalable dual input DPD approach, because we know that the PA is only sensitive to this signal and this signal. So the DPD also only needs 2 inputs. On the other hand, we need to have a crosstalk model, which actually is a replica of the antenna. So the crosstalk model is connecting the different branches to the different antennas. And this works as well as a multi-input DPD, and it has much lower complexity. So this is a very nice approach that I recommend you to look into. All right, I have a few minutes left, so I want to spend those on the last topic, which is not really a circuit or antenna oriented, but it is more going into system level. Because what I talked to you before about phased arrays and active antenna systems, this is the direction to go for millimeter wave, for example, right now. But there is also a trend nowadays moving from single antenna or single co-located MIMO systems to distributed antenna systems. And we are interested in ways of testing that. So if you take a traditional co-located system for 5G or 6G, this is how it typically goes. You can do beamforming to increase capacity, efficiency and reliability. But the problem is that there's a high correlation between different channels, and there's also a big risk that if there's some blockage, you cannot really get the high efficiency that you, high coverage and high capacity that you want, particularly for high frequencies. So it is therefore very advantageous if you can have a distributed antenna system where the users can be reached from different sites. And if they are collaborating, we can get the same gains as you did in the co-located case, but a much better uniformity. The challenge is, however, to make these different distributed antenna points coherent, and that's a fundamental challenge. So what we have done is to explore what is called sigma delta over fiber, and let me just quickly review what this is about. It is about encoding a communication signal on a high-speed digital optical fiber link. If you take a communication signal, take this example, we convert it into a bit stream using a sigma delta modulator. We do a digital up conversion to a high frequency, and then we quantize the signal into a bit stream. And the quantization is done by a sigma delta modulator operating at a very high frequency. So for example, this could be 10 or 20 gigabit per second. So with that high oversampling, we could encode a narrowband communication signal with relatively high fidelity. The advantage is that in the remote radio unit, which it could be tens or hundreds of meters away, we can then recover this communication signal from a bandpass filter. So actually the coding is done such that all the distortion created by this binary clipping is moved out of the band of interest. So if we keep that one, we can recover the communication signal. The other advantage is that the phase of that signal, RF phase, is not given by the remote unit, but by the clock of the central unit. So if we have multiple remote units, they will be all derived from the same clock of the central unit. There is no oscillator at the remote unit. So that means that we can do beamforming and phase arrays and so forth easily. So here's a test bed that we made with 12 channels at 2.35 gigahertz. So a central FPGA, and you see 4 channels here, but actually we have 12 channels and 12 remote antenna units connected to each central unit. The remote antenna unit has this optical link, bandpass filter, amplifier, and antenna. Okay, so that was very interesting. So we wanted to do experiments, and here you can see in our office environment, the red boxes are measurement locations. We have a kitchen, we have a conference room, open office area. To make it efficient, we actually designed a measurement robot, and the measurement robot was then traveling in this area and captured data. So here is a picture of the measurement robot designed to follow stripes that we made on the floor. So based on the collected measurements, we could do channel estimates and communication experiments in an automated way. And then we can also compare if we put all of the antennas in one place that would be co-located, or if we distributed antennas that would be distributed MIMO. And here you can see to the right a comparison of the user capacity as a function of the position. And as you can see, obviously the distributed antenna configuration has consistently much higher capacity than the co-located case. We could also use it for localization experiments. So here we put in access points in an anechoic room, and we placed different user equipment here and managed to locate the physical position accurately. Better than 0.2 meters, which is very good resolution given the narrow bandwidth that we have. Finally, we are now scaling this up to millimeter wave. So we're developing an architecture for 28 gigahertz, using again a central unit and radio over fiber, digital radio over fiber, but now higher speed interconnect, 25 gigabit per second, and 4 channels in the same radio unit. So using that transmitter, you see 4 individually driven antennas, we can do digital beamforming. It's a very busy picture, but you have actually a transmitter antenna here with 4 channels and 2 receive antennas here. So we can then send independent data to the 2 users and study how the linearity and how the bit rate can be controlled, or how much capacity we can get. Here you can see the NMSE, that's the user user data error for the 2 users as a function of symbol rate. So even up to 500 mega symbol per second, I think this is 64 QM, we have very good signal quality and we have very good NMSE. So the results here demonstrate that we could actually have very high capacity for 2 users simultaneously. And this is work ongoing, and we are still trying to expand this for millimeter wave, further millimeter wave work. And that actually brings me to the end of my talk. So if I should wrap up, transmitter design is today a cross-disciplinary topic. Power dissipation is a great challenge, both for energy consumption as a whole, but also for heat itself. The integration of antennas and the circuits in a dense area gives rise to new distortion phenomena, requiring complex algorithms to correct for it. and therefore understanding linearity and power dissipation effects is critical for successful transmitter design. And finally, towards distributed antenna systems, we need to investigate hardware impairments even more by using advanced test beds, as I showed you at the end. So here I would like to acknowledge some of the colleagues that have worked with me and my team over many years to get the results that I reported. And by this, I would like to thank you all for listening, and I'm happy to take questions. Do we have any questions here? Let me see. You can put it on the chat, or you can unmute yourself, please. In Doherty PA, I can read a question here. In Doherty PA, how do you perform low pull for the amplifiers connected through a combiner for both the cases, case 1, while the peak amplifier is turned off? I'm not sure if I understand exactly which part you refer to, but let me see. I guess, are you talking about this part? I can probably say that the load pull data that we need to design the combiner is not obtained when the amplifier is inside the circuit. The load pull is done on the transistor itself. So we take this transistor as an example. We perform load pull of that individual transistor, not in the measurement, but in the simulator typically. So we have a transistor model and we do load pull simulations, and from the load pull simulations we get impedances in peak power and in back off for the main and auxiliary, and from those impedances we can derive this combiner network. Okay, was that clear? And I should say also that low pull is one thing, but also actually the off-state impedance of the auxiliary is also taken into consideration. How about distributed amplifier concept for better efficiency? Well, there are many distributed amplifier concepts. There is one I know about from Ericsson. They call distributed efficient power amplifier. It's actually a distributed amplifier, this traveling wave amplifier. It's not a distributed amplifier, but it is designed in a way such that the impedances add up to, or the signals add up coherently. So it's not really a load modulation involved, but it is only power combining made in an efficient way. But I'm not sure if that answered the question, because how the distributed amplifier for better efficiency. I'm not exactly sure if I answered the question, but there is something called distributed amplifier by Ericsson.
The main problem is for such cases when the power amplifier takes different values for different channels.
Yeah.
So that need to be distributed properly to get a best efficiency. That is why they go for a distributed concept. So okay. How is the advancement in this?
I am not probably fully updated on the recent developments in this, but I could imagine that what I have seen in the literature is more or less ideal concepts where the output capacitance is taken into consideration in the distributed amplifier. But if obviously this is only an approximation, and at high frequency it is more complicated than that. So I'm not sure how, I'm not actually aware of how this could be done or exploited for new concepts.
This is one major area of interest for research.
I completely agree. I think that could be very interesting. And maybe one could do something based on the low pull approach here that we have. If that could be extended for distributed amplifier, that could also be very interesting probably.
Thank you.
I also read that what are some of the strategies to reduce mutual coupling and its effect in MIMO systems in 5G? 2. Are the DPD algorithms real-time adaptive based on channel? Okay, I can answer the second part. Are the DPD algorithms real-time or adaptive based on channel? And my quick answer is no. We have not performed research on real-time implementations of the algorithms. It is in fact a very important topic, in my opinion. There is very little done on how to implement adaptive real-time DPD, and I think it's also because the effort to do a real-time DPD implementation when it comes to FPGA programming and so forth is quite large. I believe that it would be good if there could be more advancement in this field, but I know that there are some techniques that we have published on how adaptation can be emulated by measurement techniques, but I think that's a very good area for research, how to adapt quickly. Because actually, when you switch, for example, from transmit to receive, or sorry, from receive to transmit, there is a need to very, very quickly establish the linearity of the transmitter. So that puts stringent requirements on the adaptation techniques that you use, and I think there is need for more research on that. There was also another one. What are some of the strategies to reduce mutual coupling and its effect? Well, to reduce the effect of mutual coupling is twofold. First, you may look at the antenna, try to see if you can design antennas with less mutual coupling. There I know that it is an active field, but I also know that there are fundamental limitations on what you can do. So it also comes down to power amplifier designs. So it is a big interest on architectures, power amplifier architectures that are less sensitive to load mismatch. And that's also something we work on, but I don't have anything to show right now.
Any other questions? Any? Any other questions? I think we have to conclude the session. We have to conclude the session if there is no any other questions. Hello? Is my voice audible? Hello?
Yes, you are.
Hello?
Hello?
Yes?
Yes. I think, sir, is there no more questions, so we can conclude the session. And thank you, sir. Thank you once again for accepting our invitation for the invited to.
Thank you very much. It was a very big pleasure for me to have the opportunity to present to you. If any of you are interested to know more, and if you want to discuss something, don't hesitate to let me know, and we can follow up afterwards. Otherwise, I hope to see you.
Thank you, audience, for joining our event.
Thank you very much.
Thank you, sir. Thank you.
Okay, thank you. Goodbye. Have a nice evening.
Bye.
Bye.